This is Geometry, Lesson 9-3, Similar Solids. Our objective today is to find volumes and surface areas of similar solids. So first, I want to talk about the length, area, and volume of different scale factors. So in general, when a problem tells you that we have a scale factor, that scale factor is really, I'm going to write this down here, you have to add this additional, this is technically the length. GTH, I can spell it, length. The length scale factor. By default, every single scale factor is assumed that it is the length scale factor. However, there will be a different scale factor for area and volume. You'll always need to convert the volume scale factor into the length scale factor, or the area scale factor into the length scale factor. You always assume we have a length scale factor. So in this first example, I'm going to tell you the scale factor to get from this cube to this cube is 1 to 2. Again, you do a colon to say we're doing our start shape and then our end shape. We can put any numbers we want here as long as they're integers. I mean, I guess you could use decimals, but usually these are whole numbers. So notice what we did for the length. Again, this is a length scale factor. So this length of 2, you can count the 1, 2 squares, right? Turn into 4. 1, 2, 3, 4. Every single length, you just multiply by 2 because this ratio is 2 to 1. Or I guess 1 to 2, but you do this number divided by this number, the end divided by the start to find your scale factor. The new divided by the old, in other words. So therefore, all these new lengths are 4. That seems like it's easy, but it's about to get tricky. So what is the area of any of these shapes? I'm going to randomly choose this face right here, which is a 2 by 2. So therefore, this area is 4. So I'm going to come back here and say, you have an area of, I'm going to do this in black. This area is 4. Well, what was the area now over here? If I come back with my laser pointer and say, okay, well, this is 1, 2, 3, 4. Again, that makes sense, 4. So this is 4 by 4. This area of this square is 16. So if I come back over here to my pen and say, this is now 16, which is interesting because how did I get from 4 to 16? I did not multiply by 2. This is a different scale factor. This is the area scale factor. The way that area scale factors work is we square it. We take it to the power of 2 because area is in the second dimension. So instead of saying 2, we're going to say 4 because, again, we take it to a power of 2. So this 2 is really, if I zoom in here, is really 4, which is really 2 to the power of 2. This was 2 to the power of 1. And you can already see where I'm going to go with this. Let's check out the volume. So the volume of this original shape is 2 by 2 by 2. So if I multiply all of these dimensions together against the length, width, and height, I get 2 times 2, which is 4, times 2 again, which is 8. The original volume here is 8. So let's come and mark that with an 8. The volume over here, if I multiply each of the dimensions by each other, I'm going to get 4 times 4 times 4. 4 times 4 is 16, and times 4 again is 64. So we're going to say that this is 64. So how do you get from 8 to 64? Well, from 8 to 64, I multiply by 8. And 8 is the same thing as 2 to the power of 3. So in other words, in order to find the volume scale factor, you can start with the length scale factor and take that factor to the power of 3. Take this one to the power of 3, this one to the power of 3, and that will tell you truly how to convert. If you want to find the area scale factor from the length scale factor, you take each of these to the power of 2, and if you're just talking about the length, which we never really are in this lesson, then you can just leave it as a scale factor of 1 to the power of 1 and 2 to the power of 1. So before I move on to an example problem, I just want to make sure you understand the general formula of how to use a scale factor. If I have a scale factor, I multiply the original shape. If it's the length, area, or volume that I'm talking about, it might be scale factor squared, or it might be scale factor to the power of 3 if it's volume, right? I multiply the scale factor to the original to get the new. And sometimes I'm searching for the scale factor, and you can see in this equation up here, if I divide both sides by the original, that's an O, not an 0, then I'm going to get this formula that says it's really the new divided by the original. New divided by original. All right, so that will help us to do example 1 and 2 because it's asking for the scale factor. So the scale factor is really asking for the linear or the length scale factor. So what we have here is a area scale factor. So the general procedure here is we're going to say, okay, it's going to be the new divided by the original. It's the new divided by the original. So I'm going to say over here, I really have this fraction of 100, I'll say new over the original. which is the same thing as 125, what was it, over 80, right? Over 80. I'm going to ignore the units for a sec because they cancel out. Meter squared and meter squared cancel each other out. So the first step is to reduce. Again, I can divide the top and bottom here by 5. So if I divide by 5 and divide by 5, you'll get your reduced fraction. And here's a pro tip. I'm letting you use a calculator on everything, so you might as well learn how to use it. Your calculator will automatically reduce if you're using the Desmo Scientific Calculator. If I type in 125 divided by 80, it gives you 1.5625. But if you hit this little fraction button on the top, right of that, it tells you that reduces to 25 over 16 in its most reduced form. I just happened to know that I needed to divide by 5 in order to get that, but that is exactly the reduced fraction. Now that we have the reduced fraction, we know that in order to go backwards, the original scale factor was squared, so to undo the square, I need to take the square root. So this, and I'll write this down for us in our notes too, this right here is the scale factor, but it's the area scale factor. In order to get backwards from area to length, we have to take the square root. So the square root of 25 and the square root of 16, this will turn it back into the length, L-E-N-G-T-H, length scale factor, which is 5 over 4, which means we have a 5 to 4 ratio. And again, usually we put the original on the bottom, so we'll say it's a 4 to 5 ratio. So over here we'll say 4 to 5 ratio, which makes sense because in this original problem, I had the small one first, small one to big one, 1 to 2, right? Small one to big one, so it's 4 to 5. That all makes sense. Make sure that the correct size is on the correct side. All right, let's try another one, but this time with volume. So this one was with surface area, these are with volume. So again, the general idea here is we are going to write this out, and we're going to say, we're going to do the new over the original. And that's going to be, the new shape is 810 feet cubed, and the old one is, oh my God, 15,360. Let the calculator do the heavy lifting here. So this is going to be 810, know how to use these tools, divided by 15,360, make that into a fraction. Okay. I'm just going to say it equals 27 over 512 in its simplest form. And then this is, again, the volume. This is the volume scale factor. I'm going to put SF for scale factor because I'm getting lazy. So in order to get from a volume scale factor to the length scale factor, we have to take the cube root. So I'm going to take the cube root of each of these, So this is how you do that on the calculator. You hit the N power button here, and then I hit 3, 27. Okay, the cube root of 27 is 3, which you probably already knew. The cube root of 512 is 8, but I want to just double check. So it's cube root of 512 is 8. Okay, so I knew what I was talking about. And then finally, I put it in the correct form. So it's always going to be big to small in this case because it's this to this. So it's going to be 8 to 3 in this case. We're going to say this one is an 8 to 3 ratio. All right. Let's do another example. So in this one, I need to find the surface area and the volume of the larger shape. And I know it doesn't matter what the shapes were, by the way. I just randomly selected the shape. Like, as long as I give you a V, as long as I give you a surface area, it doesn't really matter what shape you have. In this case, I chose a random shape. I have no idea what shape it is at this time. And I know that the scale is not something nice. It's 7 to 9. And I have a surface area, I have a volume. I need to convert each of these. So I need to find the surface area, or I guess the area scale factor. So let's go ahead and find that. So we're going to say the area scale factor is going to be a number here, and I'm going to write the volume scale factor down here. So the area scale factor, normally you're always doing, and again, I'm coming back to my formula. Whenever I have my ratio, it's going to be new divided by the original. In this case, the new is this one, the original is this one, right? So the new divided by the original, so 9 divided by 7. So this is going to be 9 divided by 7. And this makes sense, by the way. Sometimes I get students that say, okay, which way does it go? Is it the 7 on top or is it the 9 on top? Well, is it supposed to be getting bigger or smaller? This is the original. That's going to be the newer. Oh, it needs to get bigger? Then the bigger should go on top. If it needs to get smaller, then the smaller should go on top, right? So this is just the linear or the side length scale factor. In order to make this an area scale factor, we need to take each of these to the power of 2. to take the volume scale factor, we had 9 over 7, and we're going to take each of them to the power of 3. That means the area scale factor is going to be 81 over 49, and that means the volume scale factor is going to be 9 cubed, which I don't know off the top of my head. It's 729, and then 7 cubed, which is 343. So now we know what fraction to multiply by. We had our surface area, so I'll say this is going to be the original. The original surface area in this case was 392, and we're going to multiply that by the scale factor for the area, which is going to be 81 over 49. And we're going to get our answer here. So I'm going to say 392 times 81 divided by 49, and we get 648. And make sure our units are correct. So this was in meters, so this is going to be in meters squared for one of the two answers. And then down here we had the original volume, which I'm going to rewrite, which is 3,087, and we're going to multiply this by 729 over 343. On the calculator, we're going to do this over here. 3,087 times 729 divided by 343, and that is 6,561. Again, what units are we in? To power of 3, because we're in the third dimension, we're in volume. All right, so just to make sure that this makes sense, we had, and this is the sanity check, right? We had something small and we're getting something bigger. So did I get something bigger from 392? Yeah, 648, that seems a bit bigger. 3,000 turned into a 6,000, that seems a bit bigger, that seems right. It feels weird though, because this seems like double the volume, and that's just the nature of how scale factors work. They get really, really big for volume and not so big when you're talking about just lengths. They get proportionally bigger and bigger. There's a fun little factoid that maybe I'll talk about if you guys get me off onto a tangent. Talk to me about why it's impossible for giants to exist. And spoiler alert, it's density. Like they'll fall apart. All right, example 4. Find the missing value. Okay, so in this one, it doesn't tell us the scale factor. So we first need to find the scale factor. We'll take that scale factor to the power of 3 to get from u to u. But the first step is, how did we get from 20 to 980? So again, I'm going back to that original formula. I'm going to do new divided by original. So the new shape is this solid 2, which is 980. So I'm going to write this down. The new shape divided by the, I want to say old, but I guess it's the original shape, right? By the original shape is going to be 980 over 20, and this is all an area, so I'll remember that, but let's go ahead and have the calculator simplify this for us. 980 divided by 20, and then we'll turn it into a fraction. Oh, it's just 49, so 49 over 1. 49 over 1, which means, and this is the surface area, by the way, so this is surface area. To get this back into the length, man, why do I keep spelling length this way? To get it back to the length, I need to take the square root. So I'm going to go ahead and square root each of these, and this is going to turn into 7 over 1, which means we were multiplying by this number. We were multiplying by 7. 7 squared to get from here to here, and 7 cubed to get from here to here. So this is the length scale factor. To find the volume scale factor, we'll say that this is the volume. This is going to be off the page if I don't squeeze it in here, huh? So this is going to be the volume scale factor will be the 7 over 1, but each of them will be to the power of 3 because volume is in the third dimension. This is going to be multiplied by the volume that we originally had, which is 13, and that will be equal to our answer. So this is going to be 13 times 7 to the power of 3. 7 to the power of 3 is 343. And this times 13 is 4,459. 4,459. And that's in meters cubed. Meters cubed. This unit, more than any other unit that we've done so far, the units are important. All right, and our last example for the notes. This time I don't know the surface area. So last time I knew surface area and was trying to find volume, and now I'm doing it in reverse. I am trying to find that surface area. Okay, so I need to find the scale factor. I need to know how to get from here to here, so I'm going to use these two to help me figure it out. Again, I'm always going to do the right divided by left. That's typically the way that most things work in math. So I'm going to say that the new versus the original is going to be 16 over 11,664. Geez Louise. All right. So what is this fraction going to be? 16 divided by 11,664. Turn it into a fraction, please. This is equal to 1 over 729. Again, this is the volume scale factor. So to get from the volume scale factor to the length scale factor, I'm going to cube root the top and cube root the bottom. So when I cube root 1, that's just 1. Okay, cube root of 729. Doesn't that look familiar? 729. We saw that before. Where do we see that? Right there. That's 9 cubed, right? So I can come back here and say, this is 9, 1 over 9. So that's the length scale factor. And now I'm going to find the answer, right? So we had the original number that was 729, and we're going to multiply this by the length scale factor, 1 over 9. But because it's in the second dimension, both of these are going to be to the power of 2. So really what I'm doing here is I'm doing 729 divided by 81. So if I do that, 729 divided by 81 is 9. So our answer here is we get 9. Make sure our units are correct. We're in centimeters, second dimension, so power of 2 centimeters squared for our final answer. All right, that concludes lesson 9-3 for similar solids. Thanks for watching.